right, so we went from ketones and aldehydes all the way to acetals. We didn't really talk too much besides saying what a hemiacetal was. We didn't really talk much about hemiacetals. What's the deal? Well, hemiacetals are usually unstable. On your course packet, I say they will always produce either the acetal or carbonyl, except when they are blank. Except when they are cyclic is the answer. Cyclic. Oh no. Cyclic. Okay, so let's step back for a second though. So where else did we see hemiacetals? If we think about the mechanism of taking a ketone or an aldehyde all the way to the acetal, all of them go through the hemiacetal intermediate. That's what this is. It's the HOCOR intermediate. Why do they always go to the acetal or the carbonyl? Well, this is kind of the midway point. How did we drive it over here? We had excess of the alcohol. So this was kind of the rest stop on the way to the acetal. How do we go from here all the way to here? We have an excess of water. That pushes it over here, and then it pushes it all the way to there. So the hemiacetal, when we are not in a cyclic system, is kind of like the midway point going from one species to the other. That changes for cyclic hemiacetals, though. And why might the cyclic hemiacetal be favorable? The situation is that essentially it's an intramolecular reaction. So there's a very high concentration of the alcohol. I don't know why I put alcohol in quotes. This is the alcohol. And essentially when we went from here to the acetal, we said, how do we drive that forward? We have a huge excess of that alcohol and it pushes it to the right. Well, how can you have more alcohol than when it's actually attached to you? This alcohol is in an exceedingly high concentration because it's literally never too far from that aldehyde. That high concentration of alcohol drives these intramolecular hemiacetal formations to the right if it is a stable ring size. And what about entropy and enthalpy? Entropy is pretty much neutral, one molecule to one molecule, and enthalpy is the same way. It's we've been saying they're neutral. They're actually slightly favored in the forward direction, but it's pretty slight. So we'll continue saying that it's pretty much neutral. So how does this happen? What would the mechanism look like? It's the same mechanism that you would see kind of as we progress through those things. We have acid catalysis around. We'll say that that's H3O+. The ketone or aldehyde grabs that proton. That enhances the electrophilicity of this carbon here, making this alcohol that's already attached extra attracted to the partial positive in that position. So that adds there, that makes a 1, 2, 3, 4, 5, 6 membered ring. So we're a 6-membered ring containing our oxygen. We have the alcohol there. We have this OH is that carbon, that oxygen right there. How do we get from there to the product? Well, we used that acid in the first step, and we are going to be regenerating it in the second step with our H2O. So that's how we form that cyclic hemiacetal. How favored are cyclic hemiacetals? It turns out that at equilibrium, this is 6% the acyclic and 94% the cyclic version. So they're pretty favored. It must be that this enthalpy that we've been saying is neutral. It's close to neutral, but it is favored, like I mentioned earlier. So that is driving the reaction toward that cyclic product. So now let's look at some more examples. All right, so here's our next example. I want you to first predict the product here, and then ask yourself and write something down about which side would be favored. All right, you just finished that. That's great. So this oxygen is cyclizing over there. Let's number these atoms. So 1, 2, 3, 4, 5. Now let's make a 5-membered ring. So we have 5-membered ring. This is position 5. We'll just do 4, 3, 2, 1. Position 1 is where the OH is going to be attached. I didn't say this a moment ago, but why is that a wavy bond? It's because the oxygen can add to the front face or the back face, and that's going to result in different stereochemistry at that position. So it's going to be both the wedge and the dash, so that's why it's a wedge. It's a wavy bond there. What about this at position 3? The stereochemistry is not going to change. It should be the same. So is that going to be a wedge or a dash over here? And what it's important to see is that essentially 2, 3, 4 is directed this way here, but it's the opposite way here. Like it's making a peak here, 2, 3, 4, but if we flip that over, 2, 3, 4, what happened to that wedge? Essentially that wedge was like that, but when we flip the molecule over, now it's going to be a dash. So that's what we would see right here, is the dashed CH3 because we flipped that carbon over. It might help you even to make a model of this to kind of see how that changes if you're having a hard time with that whole flipping it over idea. Moving on to another one. One other thing that I didn't mention that you can also do to make sure you are at the same ending stereochemistry for a carbon that nothing happened to in the reaction, figure out R or S. This stereo center is R over here. Nothing happened to it. It's still R over there. So again, if you're having a hard time with the flipping things around idea that I mentioned right here, R and like the RS can help with this process. All right, here's the next one right here. We wanted to predict the product and then say which side is favored. On the last one, which is right here, I didn't do the second part, which side is favored. It turns out that this is 89% at equilibrium. This is 11%. So 6-membered rings are highly favored. We had the 94%. 5-membered rings are still very stable ring structures, 89%. So what's going to happen with this one here? So pause it, figure out your product, come back. Okay, so same process as last time. 1, 2, 3, 4. We number our atoms of the ring. That means we're going to form a 4-membered ring. That ring looks like this. We have the wavy stereochemistry there, and the CH3 there becomes a dashed CH3 there. Is this one favored or not? Which side is favored? Good job. This is a 4-membered ring. 4-membered rings are strained, so while this is the favored side here, this is the highly favored side over here. So that is that. One last topic. All right, so this last question just says, how did this happen? And essentially, if you're having a hard time with this, and you should definitely, how did this happen? That is code for draw the mechanism. You should be able to figure out a mechanism for this reaction. And if you're having a hard time doing that, this is a hemiacetal. This is an acetal. What did we say at the beginning of this video? All ketones or aldehydes go from the carbonyl to the hemiacetal to the acetal. So we've already worked through this mechanism. It just looks a little bit different because it's cyclic. You might just not be used to seeing it that way. Okay, so Yeah? All right, you already worked it out? That's good. That's good. So just like on the acyclic system, we need to form a good leaving group from our water molecule. There's catalytic acid around. So that is going to protonate our OH, making it a good leaving group. And at that point, the water molecule is just going to leave. That would provide us with this carbocation, which doesn't look all that stable, but we have to remember that it's not just that carbocation, it's also stabilized by resonance. This is a 6-membered ring, I promise. So at that point, the oxygen is the positively charged species. What is nucleophilic and is around? Well, that water molecule is around, but also we are in a boatload of ethanol. So there's a lot more ethanol around. That's more likely to add in to this species to make the oxonium ion version of our product. All we are is one step away, one acid-base transfer. We use the acid there. We're going to regenerate that acid in our last step. It's just going to grab that proton, and we have now formed our product. So hemiacetals, cyclic or acyclic, if they are in an alcoholic solvent, so ethanol, methanol, isopropanol, they will proceed to the acetal just like an acetal would form with an excess of alcohol in an acyclic system. But it's just the hemiacetals themselves, even in water. Remember, water is how we collapse an acetal to the ketone aldehyde, or in this case, a hemiacetal. So if we had an excess of water, it would push it back this direction. But if we have the alcohol as the excess, it's still going to push it toward that acetal. So it's just a cyclic acetal. So I feel like I've said it a bunch of times. I could go back and look at the video, but I'm just gonna move on with my life. All right, bye-bye.